So, solving exponential functions. Start with a quick review of exponents. So, simplify and express with positive exponents. So, when we multiply powers with the same base, what do we do with the exponents? What do we do with the 3 and the 12? Add them, right? So we multiply powers with the same base, you add the exponents, and we get x to the 15. Okay? When I take a power, and so this exponent thing, this whole like x cubed, right? I mean, this is called the base, and this is called the exponent, and the whole thing can be called a power. Yes? No. So, you can copy it down. I will post this afterwards, so you can just print it off if you want. I thought about that, but then I realized, like, why waste the paper kind of in printing this off for you, right? So if you want to copy it down, just write down the stuff. But you can print these off afterwards, like 2 sheets. So I'll save this as a PDF. You can print that off. And the video will be up, so if you want guidance through that PDF, again, like, so if you missed a class or something and you're looking for this, then, print it off and then just sit down and go through it, go through the video, or skip forward to that part. You might say, I don't need this exponent stuff, I know that, but I wanted to see how you did such and such a thing. Okay? Power to a power, what do we do with the exponents? Wow, full house. Oh, not quite a full house. Multiply the exponents, right? Okay, so what do we get? X to the power of 18, right? So power to a power, multiply the exponents. And this exponent law stuff comes in over the next 2 units, right? It's this unit on exponents and then one on logs. 5x cubed over x to the 4th. We're dividing. What do you do with powers when you divide? Minus them. So it's 5x to the 3 minus 4, which is 5x to the negative 1. But we need a positive exponent, so it becomes 5 over x. Right? So if you have a negative exponent, you just move it from where it is to where it isn't. If it's on the top and it's negative, you move it to the bottom, it becomes positive. If it's on the bottom and it's negative, you move it up top and it becomes positive. Okay? Then we get a positive exponent. And last, this, 2x to the negative 3, all raised to the power of 4. What do we do there? So, what's the answer? 2x to the, yeah, is that it? No, what is it? So, when you do power to a power, everything in the brackets gets raised to that power. So the 2, which is a 2 to the 1, becomes 2 to the 1 times 4. Okay, so power to a power, we're multiplying like we did here, but it's everything. So this works out as 16x to the negative 12, which, if I do positive exponents, is what? 16 over x to the 12th. Okay, so watch out for power to a power, especially when there's like a number in there, because that's where people go wrong. They just write the 2. They do the variable fine, right? You'll get 2, but you use the 2 instead of 2 to the 4th. And remember, what this really means is, it means 2x to the negative 3 times 2x to the negative 3 times 2x to the negative 3 times 2x to the negative 3, and do that 4 times. Believe it or not, that paper has nothing to do with you. Not this sheet, and it doesn't have your name on it. I'd have given you one if so I'm not handing these out anymore, right? But I will save the PDF of this when I'm done. You can print off the notes if you want. You can write down what I'm doing. If you like to copy stuff down while I'm doing it, that's cool. Okay? I don't know what to do for this bit here, like, if you want to write it all out. But okay, solving exponential equations. Make sure you got your calculator out because we're going to need those in a moment. Chessboard has 64 squares. Everybody's seen a chessboard, right? Or checkerboard. There's a fable that says the inventor earned grains of rice in payment for his work in inventing it, right? So he said, basically what he said is, I'd like 1 grain of rice on the first square, 2 grains of rice on the second square, 4 grains of rice on the third square, and then just keep doubling it until we reach the 64th square. And the king, who hadn't really taken math classes at all, agreed to this and said, sure, okay, we can do that. Represent this relation in the form. So it is an exponential equation. X represents the square number, so which square, square 1, square 2, square 3, etc. Y represents the number of grains of rice on that square. So how many grains of rice are on the first square? 1. And then what happens as we go to each square? What are we doing to the number of grains of rice? Doubling them. Okay, so we're starting with 1, and then we're doubling. That's the amount by which it's increasing. And we've got this power of x minus 1. So when we put a 1 in for the first square, 1 minus 1 is 0. 2 to the power of 0 is 1. Times 1 is 1, right? So this expression works. Let's try it out again. I want to make sure I've got the right expression, right? So you're doing a problem. You want to, okay, let me try this for a couple of squares. On square number 2, 2 minus 1 is 1. Okay, we're not going to worry about the 1, right? Just multiply by 1. So 2 minus 1 is 1. 2 to the 1 is 2. On square number 3, 3 minus 1 is 2, and 2 squared is 4. Okay, so that's working, right? I expect 1 grain, then 2 grains, then 4 grains, and so on. Determine graphically which square on the chessboard would correspond to 128 grains of rice. Okay, so we're going to pull out our calculator, turn it on. We're going to go to y equals. We're going to enter this equation. We don't really need the 1, right? It's 1 times anything. But we could write it in. So 1 bracket 2 bracket to the power of, and then we go x minus 1. Now, if you're using the newer calculator, this is what you'll see, right? If you have the new firmware. If you're using the older calculator, then what I might want to do on that one is just throw a bracket in here and go to the power of x minus 1 and close the bracket. Okay. I don't need that on this calculator because I can see what it's doing, but I just want to make sure that we're not doing this, right? That we're not entering accidentally y equals 2 to the x minus 1. Okay, so you just have to make sure that your calculator, so by doing it this way in the calculator, y equals 2 to the power of x minus 1, then we're making sure that all ends up as the exponent. Because if we don't have it, if you could see it the way I entered it, you could see, yeah, that was the exponent, was x minus 1. On the older calculators, you won't necessarily see that. In y2, we're going to put in 128, because we want to know what's the x value when y is 128, right? Because y is the number of grains of rice. And we can hit graph. And we're not going to see too much. Well, there's our exponential function, right? We know what that looks like. We've been, that was the last section. We looked at that. So we know I don't need any negative y values because we know y has to be greater than 0. I don't, in this case, under this context, I don't need any negative x values. So my x's can start at 0. X max, maybe 10 is good. I'm not really sure. X scale of 1 is good. Y min, I can start at 0. Y max, I have to at least show 128. So let's go to 150. And the scale, say by, I don't know what, 15s? And using these window settings, we'll hit graph. And first it graphs the exponential. It starts out kind of low, but you can see it jumps up pretty quick. And then we get the y2, which is 128. So we want to know what's the x value when y is 128. We can almost count it off of here, but we'll do an intersect. So second calc intersect, first curve. So what I like to do is just move along the curve until I'm at the point of intersection. or close to it, and then hit enter 3 times. So first curve, I've got my 2 to the x minus 1. Second curve, I've got the y value of 128. And then a guess, and we get that x is equal to 8. Okay. So determine graphically which square on the chessboard. We get x is equal to 8. So we're looking at the 8th square, right? Because the x value, x represents the square number. So the 8th square. The 8th square has 128 grains of rice. Any questions so far? Good. Solve algebraically for the square on the chessboard that would correspond to 256 grains of rice. Okay, so we have, okay, we don't want that, right? That's not what we want. So we have our equation, y equals, I'm going to drop the 1, right, because we don't need a 1 in front. Y equals 2 to the x minus 1. So we're going to write 256 is equal to 2 to the x minus 1. Now, in order to solve this, we need to write 256 as a power of 2. Okay, so we got to figure out 2 to the what is 256, right? I'm going to say 2 to the what is 256. Sorry. We'll do that over here. 2 to the what is 256. So you can play with your calculator and say, okay, what's 2 to the 10? That's too big. 2 to the 8, that's too small, or whatever. 2, 4, 8, 16, 32, 6, 4, 1, 22, 6. 2 to the 8. Okay, you can count on your fingers. You can go powers of 2. So we know that 256 can be written as 2 to the 8th. So we go back here. Instead of 256, we write 2 to the 8th. If 2 to the 8th is equal to 2 to the x minus 1, what can we say about x minus 1 and 8? What do we say about these two things here? They must be the same. Right? They've got to be equal to each other. So we drop the 2's. We say 8 is equal to x minus 1. So x, add 1 to both sides, is 9. So the 9th square. Questions? I know you're curious, right? I mean, you want to know, like, so how many grains of rice are there on the 64th square? Well, you should. It'll be 2 to the power of 63, which is 9.22 times 10 to the 18th. Now you figure 10 to the 9th is a billion. 10 to the 12th is a trillion. 10 to the 15th would be a quadrillion if there were such a thing. 10 to the 18th would be a quintillion. Wow. So, lots. Yeah, more rice than there is on Earth, and it never has been and never will be. So things go pretty quickly. There's another variant of this problem, which is the allowance problem. And it's like, you know, little Johnny's parents are trying to decide what allowance, and little Johnny, who took math, suggests, well, how about you just pay me a penny the first day and then just double it, so I'll get 2 cents on the next day, and then 4 cents, and then 8 cents, right? It's not like much. And then by the end of the month, of course, it's a pretty large sum of money. So. Okay, part C. We're going to solve algebraically using a common base. So what we need to do is ask ourselves, can 128 be expressed as a power of 4? So you think powers of 4, right? 4 to the 1 is 4. 4 squared is 16. 4 cubed is 64. 4 to the 4th is 256. So I cannot write it as a power of 4. But we know 128 is a power of 2, right? Because we just did that. So I can write 128 as 2 to the power of 8. Right? Again, you may be playing with your calculator, figure out 2 to the what, 2 to the 7th, no, that's like 64 or so. First of all, 32, is it 7? 2, 4, 8, 16, 13, 64, 120. Sorry, 2 to the 7th. Is 128. It was 256 that was. Now, how do we write 4 as a power of 2? This should be easy question. 4 is equal to 2 to the power of 2, right? 2 squared. So we're going to write 4 and 128 both as powers of 2 so that they have a common base. We're going to use power to a power. So what do I do with these guys? Multiply them, right? So what do we get? 2 to the power of 6x minus 2. And that's equal to 2 to the power of 7. Yeah, 2 times 3x minus 1 is 6x minus 2. You got to use distributable. What can we say about 6x minus 2 and 7? They're the same, right? So it's, we got 2 to the power of this is equal to 2 to the power of that. That means this and that have to be the same, right? So we say 6x minus 2 is equal to 7. So 6x is equal to 9, and x is equal to 9 over 6, which reduces to 3 over 2. Okay, so x is equal to 3 over 2. Now, the end of the test comes, you still have some time, you want to check this and say, how do I know that's right? Well, you go 4 to the power of 3 times 3 divided by 2, right? Because I'm thinking x is 3 over 2, minus 1. It'll do order of operations, right? It'll do the 3 over 2 multiplied by 3 and then subtract the 1. When I hit enter, what should I get? 128. So 2 thumbs up, right? So it's been correctly solved, right? We know that x is 3 over 2. Next one, can I express 625 as a power of 5? 5 to the 4th? Yes. Okay, so we got 5, 25, 125, 625. So 5 to the 4th. Now, it might be handy if you knew your powers of numbers, right? Like your powers of 2, powers of 3, like 3, 9, 27, 81, 243, 729. I'm not suggesting you memorize them, but just be able to recognize that, oh, 343 is a power of 7. I don't know which power, but I'm pretty sure it's a power of 7. So then you can play with 7 to different powers till you get 343.
I can't remember, but isn't there a trick for powers of 9, like something about the digits adding up or something?
They'll add to 9. Well, wait a sec. So 9 squared is 81, so 8 plus 1 is 9. 9 cubed is 729, which 7 plus 2 is 9, plus 9 is 18. So they may add up to 9, but
okay.
Yeah, something like that. Just kind of try and recognize different powers so that you can say, oh, yeah, 64 is a power of 4, right? Even if you need to use your calculator to figure out which power it is, that's okay. All right, what do we say now? X plus 1 equals? Come on. What's x plus 1 equal to?
4.
4, right? This has to be equal to that. What's x equal to? 3. Okay, solved. 8 to the 3, 8 and 16. Okay, 16 can be written as 16 or 4 squared, or what can we write both 8 and 16 as a power of? Okay, so 8's not a power of 4.
Oh no.
So go lower, go 2.
I'm so bad.
That's okay. What's 8 as a power of 2? 8 is equal to 2 to the power of? 3. So we replace the 8 with 2 cubed, and then that's going to be raised to the power of 3x. We're going to replace 16 with what? 2 to the 4th, and that gets raised to the power of x minus 1. Okay, so what we're looking for is, we're going to solve this, right, using common bases, right? We need a common base. So 8 and 16, their common base is 2. Okay, what do we get over here? 9x, right? And what do we get over here? Let's go 4 times 2. Let's go 4 times 2. Minus 4. Okay? What's the next line? 9x is equal to 8x minus 4. Which means that x is equal to negative 4. Yeah? Okay, you're just subtracting 8x from both sides. Okay, you want to check that, right? It's the old end of the test time. So what are you going to try? You're going to say, okay, I'm going to go 8 to the power of negative 3 times 4, which is that number. And I'm going to go 16 to the power of 2 times negative 4 minus 1. And when I hit enter, what do I expect to see? Expect to see the same value, right? That tells me they're equal. Well, if I did, I wouldn't get the right answer, and I have the right answer.
Because it's like 8x minus 4.
Yeah.
So to get it to the other side, would you add it?
No? If I added 8x to this side, I'd get 16x. You want to get rid of this 8x. You do that by subtracting 8x from both sides.
I thought you would like add it and then divide it.
No. We could talk about it later, but 6 to the 3x equals the square root of 216. Okay. So you've done some radical stuff. So what's the way of saying square root but saying it with a power? (216) to what exponent gives you a square root? So not squared, obviously, right? But it's how about 1/2? Right? So you raised it to 1/2, that means square root of. Okay, so now we have exponents, right? I couldn't do anything with this because that's written as a radical. You can't have this. Or we need to write everything in exponential form. So 6 to the 3x, 216 to the half. 6 isn't a power of anything, right? Like, it's not a power of 3, it's not a power of 2. So 216 must be a power of 6. So what is it? 6 to the power of what?
3.
3, okay? So you may have to play with your calculator a little bit, but you got to say, if I'm going to get a common base, then 216 must be a power of 6 in order to give me that common base, right? So you go 6 times 6 is 36, times 6 is 216, so it's 6 cubed. What do we do with the 3 and the 1/2? Power to a power. What do we do with the exponents? Add, subtract, multiply, divide, multiply. So what's 3 times a half? 3 halves. What do we now say about 3x and 3 halves?
Wait, is it 3 halves? Because that's not.
3 times a half is 3 halves.
Is it?
Yeah. So it's like doing 3 over 1 times 1 over 2. You end up with 3 over 2.
Oh, yeah.
Okay. So we know that 3x equals 3 halves. What's x equal to? We multiply 3 by to get 3 halves, which you just did. We're going to divide. So here's the thing. We need to divide both sides by 3. I really don't like dividing fractions by fractions. I don't want to have to do 3 halves divided by 3. So I'm going to flip it and say, instead of dividing by 3, I'm going to multiply both sides by 1/3. The 3's are going to take each other out, leaving me with x, and the 3's are going to take each other out, leaving me with 1/2. So x is 1/2. Okay? Need to divide by 3. Multiplying by 1/3 is the same as dividing by 3. 5 to the power of, no, 5 times. So what do we do with that 5? Now, divide both sides by 5. Let's get rid of that leading number, right? Now remember, we're looking at exponential equations are of that form, right? Y equals a times b to the x, or b to some variable, right? So this is an a value. But it's just being multiplied by this, so we divide both sides by 5. So what I want to do is isolate the power. So that is equal to, how many times that goes? 64. And 64 is a power of 2. It's 2 to the power of 6. You figured it out, right? I mean, verify that on your calculator. You just go like 2 to the 5th. No, too small. 2 to the 6th. Yeah, just right. What do we say about 3x plus 1 and 6? Okay. Once I have the bases the same, then I equate the exponents to each other, right? Means that 3x plus 1 is equal to 6. Rest up, you got to test it. 3:30. Just everybody become quiet and just stare at him. We'll see how long it takes. Once woke up in history class in grade 13 and sort of looked up and the entire class was staring at me. It was quiet. Embarrassing.
Wait, grade 13?
Grade 13. I went to school in Ontario.
Oh, okay.
It's okay. I slept through first year university, I swear. Really. Almost every class. 9 and 243. So is 243 a power of 9? So you go 9, 9 squared is 81, 9 cubed is 729. No. Okay, so what's 9 a power of? 3. So how do we write 9 as a power of 3? 3 to the 2, right? 3 squared. Now, we can do this. If it's 1 over 243, I can write that as 243 to the negative 1. Right? Negative 1 just simply says, if it's in the numerator, put it in the denominator. And in this case, there is no denominator, so this is the numerator, and you have to flip that around. 243 is a power of 3. So 3, 9, 27, 81, 243. It's 3 to the power of 5. So here we get 3 to the 4x plus 2 is equal to 3 to the 5th to the negative 1. All right? So we've taken this fraction, and we also could have done this, right? We could have written it as 1 over 3 to the 5th. Right? Which we would then write as 3 to the negative 5. So what we're aiming for here is I need this to be 3 to the negative 5. What's the next step? Yeah, so we come up here and we go 4x plus 2 equals negative 5. 4x is equal to negative 7, and x is equal to Can we check this? Turn on. We can go 9 to the power of 2 times negative 7 divided by 4 plus 1. And when I hit enter, what am I going to get? You get some decimal, and when I change it to a fraction, I'm going to get 1 over 243. Okay? What I should be getting. Part D, solving exponential equations graphically. Get out those graphing calculators. We're going to round to the nearest tenth. Tenth, how many decimal places? Nearest tenth, how many decimals?
1.
1. 100.
2.
2. Okay,
Wow,
learn
so
this.
bad.
I know, we say round because you've got 12 numerical response questions on this diploma, right? And probably about 3 of them will be that. Remember the question yesterday that said, like, when simplified, it'll be in the form a b to the x minus c over d. 3 of them will be like that, sort of the special ones. Or the other one that said, when this is this, then you get a, b, c, and you got to fill in a, b, c. You're going to see a few of the numerical response. Most of them will just be, what's the actual number, right? And so you've got to make sure that you get your rounding correct. Because you don't want to lose marks on a numerical response because you rounded it improperly. That would not be nice. Okay. Going to y equals. We're going to clear. I'm just going to clear out everything that's here. Okay, y1 is 2 to the power of 9x. If you're on a calculator that doesn't show this, I would go 2 to the power bracket 9x bracket just to make sure that it's going to, do that. And y2 is equal to 8. And I'm going to adjust my window here. 0 to 10, probably okay. I don't think it has to be quite that high. 0, this doesn't have to be 150, right? So I'll go to 10 by 1s, and we'll hit graph. Okay, 0 to 10. 0 to 10, not good for the x's, right? So let's reset our window. Let's go 0 to 2. Get a little more gentle curve. Okay, so when you're solving graphically, part of doing that is to adjust your window, right? I've got to adjust this. Okay, we're going to go second calc intersect. I'm going to move to the point of intersection. Which, wait, if y is 4,000, that's a bit too big. So you can tell my y value is like 340, right? So that's way too big. I need to be down closer to 10. Okay, close enough. That's close. I'm going to hit enter 3 times. Once, twice, 3. To the nearest tenth, 0.3. Next one, 5 to the x minus 1 is equal to 800. Going to have to readjust windows, right? So y equals, I'm just going to clear stuff. Well, this one I'll just change to 800. And we'll go to y1, 5 to the power of, that's that caret, right? To the power of. Put a bracket in if you like, right? And then x minus 1. Close bracket. I know that my window has to go to 800. And I know that power of 5 really, powers of 5 get pretty big pretty fast, so I don't need huge numbers. Let's go to 5 maybe. And 0 to, let's go to 1,000 by 100ths. And we'll hit graph. First it's going to graph 5 to the x minus 1. All right, we're close. We just need to extend out a little bit more on the window, maybe to 6. You notice what exponential functions do, right? They start off low. This first part, not much is happening here. It's pretty low, and then all of a sudden, it jumps, right? Jumps pretty high, pretty fast. Okay, let's find the intercept. So I'm looking for a value of a y value around 800. Oh, this time I can see my cursor, so I'm good. Okay, close enough. 1, 2, 3. 5.15. So what am I going to write? .2. Okay, now look, if you know you're doing a bunch, I know I'm doing a bunch here that I need rounded, so I'm just going to set my calculator instead of float, so just give me 1 decimal place. Go back to the graph. Do the intersection again, 1, 2, 3, 5.2. It'll round it for you, it'll do it correctly. If you're looking for hundredth, set that to 2 decimals. Looking for tenth, set it to 1 decimal. Last one. Oh, okay, this is a bit of a mess here. Okay, I'm just going to clear everything out. Okay, so I've got 8 to the power of bracket 2x plus 1. So make sure you're getting the same answers, right? You're trying this out on your calculator, so you know, do I have to put the exponent in brackets? Or do I have this firmware? Does my screen look exactly like that so that I don't need to do brackets? I can see that that is the exponent. Okay, so you want to try these out. 1/2, so let's just go bracket 1 divided by 2, bracket 3 to the power of, and I'm going to throw this in brackets, although I don't need to, x plus 1, bracket. Really should have been a low bracket, I think. I'm going to go zoom standard. See what I can see. A little something there. A little something there. So I'm thinking it's in around here, right? You can sort of see the two curves, which means I want to be in a little closer on here, right? Like maybe, what is that? 1, 2, 3. Let's say maybe -3 for x. -3 to, let's go to 3. And for y min, we know it can't go below 0. So let's try that.
What'd you do?
I changed the window.
I didn't see.
No, it's okay. I'll replay it for you.
Thanks.
It's okay. Gotta be faster. There's my window. So we looked at it when we first saw it graphing, and you're going to see it graph one curve at a time, and you know it's working when there's a little flashing bar up in the top right corner, right? You'll see it graph one curve at a time. When it first did it, it's like, wow, this, the graphs are really in close to the axis, to the y-axis here, and but it kind of spread out. But that's what I want, is that. So now we go second calc intersect, move to about that spot. So I'm just going to come left a little bit. And first curve, second curve, and guess. And we get -0.5. Okay, and we've had our calculator, I set the calculator so it would round to 1 decimal for us, right? So we don't have to do the rounding ourselves. Okay, any questions on these? Left side y1, right side y2. Look for the intersection. Sometimes you may want to look in the table on the calculator if you're not sure what your window should be. Go second function graph, look in the table and say, I want y1 and y2 to be about the same value. When are they getting close to each other? Right? And that'll help you to set your window so you'll know where to look. Okay? Like if we go back here, go second function table, and say, when are these close to each other? Look at this. This is 512 and 32,768. This is like 413. So I want to back up a bit, and say, well, these guys are getting really small. So somewhere in here, maybe -3 to 3 is where I want to be looking, right? Because I want these values to be about the same, and it's going to be really somewhere around there. So, oh, good, writing went away too. Part E, applications of exponential function. Yes, these are actually used in real life. Here's an application. A at t. This is how we read it. It's a function. It's the amount as a function of time, and it's read A at t, or A of t, is equal to A sub 0, which we usually call A naught. And shout out to our British heritage, right? They like to call zeros knots. And it's spelled N-O-U-G-H-T, not N-O-T, or K-N-O-T, or makes English such a fun language to learn, right? So A naught is the times B to the power of t. So A naught is the initial amount of the substance or the initial population. It's your starting value, right? It's where you're starting out at. A of t is the amount of substance or population that exists after t years, hours, minutes, whatever the thing is growing by. Okay, value of a painting increases by 4% per year. The value of the painting after t years can be represented by the exponential function. V is equal to V naught times 1.04 to the t, where V naught is the current value of the painting. If the current value of the painting is $50,000, state an exponential function to represent the value of the painting after t years. So what are we going to write? All we're going to do is put that initial value, 50,000, in for V naught, right? Or V sub 0, the initial value. Calculate the value of the painting after 10 years to the nearest $1,000. Okay, so calculate means we're going to work this out on the calculator. So after 10 years, what's T? 10. Okay, let's go to the calculator. I'm going to go mode, and I'm going back to float. I'm going to erase the little drawing I did on the screen. And we'll quit. So I want 50,000, 50, 1, 2, 3, bracket 1.04, bracket to the power of 10, and hit enter. To the nearest $1,000. So what's the painting worth to the nearest 1,000? $74,000, right? We just round. So round to the nearest 1,000, we just forget the 12 bucks, right? It would have to be 74,500 something, then that would go to 75,000, right? To the nearest 1,000. Okay, so that equals 74,000. Calculate how many years, how many complete years it would take for the painting to at least double in value. Notice the at least double, right? Because when it actually hits double, it's not going to be a complete number of years. It'll be somewhere in between. And we need it to at least double. So we're going to go to y equals. We're going to clear out whatever's in there. I'm going to put in my function, so 50,000. 5,000, 50,000, 1.04 to the x. You got to use x, you can't use t, right? And when it doubles, what's it worth? 100,000. That's 10,000, 100,000. Okay, so we're going to figure out how many years. We need to set a window for this. The window's going to have to go up to at least 100,000, right? Because we need to see that. So window. So we'll start at 0. I don't know. Let's give it 20 years. Let's just see what happens there. Y min. It starts at 50,000, so we don't have to start. You know, we can start at 50,000. Goes to 100. I want to see the 100. Let's go to 120,000 maybe. And let's go by thousands or 10,000s. Yeah, 10,000s. And let's hit graph. So that's the 50,000 times 1.04 to the x, and there's the 100,000. And we want to see what x is. So second calc, intersect. And we're just going to move until we get close. And hit enter 3 times to find the intersection. 1, 2, 3. 17.67. So how many years does it take? Big answer. How many years? 18, right? So at 17 years, it'll be below 100,000. At 17.67, it'll be at 100,000. If we want complete years, then we have to go up to 18 years, right? What if that had been 17.2 and not 17? Would we say 17 years or 18 years?
17. Oh no, 18 because it's 1.
Yeah, 18, right?
Yeah.
Yeah. So even if that had been 17.01, we still would have said you got to go 18 years, because at 17 years you would not yet be worth 100,000, right? It would still be under. It'd be like if I were to trace along. I don't know if I get to trace here. No. If I were to trace that function, then we can see when this is 17 or close, it's only 97,476. And then it hits 100,000 when it goes over. But I want it to be at least 100,000 to the nearest complete year. It's got to be 18 years. Okay, so 18 years. Okay, so even if that were 17.01, I would have to still say 18. Half-life. Who's heard of half-life? Besides the game, right? So half-life refers to a radioactive substance, right? You use it to do carbon dating and stuff like that. A half-life exponential function looks like this. So A naught, still the initial amount of the substance, but our growth now, it's not doubling, right? So what's in brackets is really our growth rate, right? You grow by 4%, that's 1.04. You're doubling, that's a 2. You got a half-life, that's a half. So H is the period it takes for the substance to divide in 2. And A of t is the amount of substance that remains after x years. This should actually be after t years. So we have this expression here, right, which is t over h. So there's some modification going on here, right? T is the time in years, hours, minutes, whatever we're measuring time in, and h is the half-life. However, everybody knows what a half-life is. It's like how long it takes for half the substance to be there for radioactive decay. So what this is, T over H is the number of half-lives, right? Because this is time and this is half-life. So if the time was 14 years and the half-life was 7 years, you'd go through that twice, right? After 7 years, you'd have half, and then after another 7, you'd have half. So this is just an adjustment, turning time into half-lives, how many of these half-lives we're going to have. So radioactive iodine can be used to determine if a person has a thyroid deficiency. A healthy thyroid gland will absorb all of the radioactivity. According to the model, A of t equals 100 times 1/2 to the t over 8.1, where A of t is the percentage of radioactivity in the blood after t days. Patients are given a capsule containing radioactive iodine to swallow. 6 hours later and 24 hours later, the amount of radioactivity is measured using a gamma probe. Using the model, determine to the nearest whole number the percentage of radioactive iodine in the blood of a healthy patient after 6 hours and after 24 hours. Okay? So we can do this just using the formula, right? We don't need to use our calculators for this. So we can say A of 6, the amount after 6 hours, is 100, which is the initial percentage, times 1/2 to the power of 6 over 8.1. Okay, so I'm not going to do any special tricks on this. I'm just going to enter it. I'm going to clear that so we can see it. So it's 100 bracket 1/2 to the power of 6 divided by 8.1. And you notice, since that stayed up there, then I'm going to go with that. So 59.8%. Right? There's 100% at the beginning. There's 59.8% after 6 hours. What was it? 59.8? Yeah, 59.8%. And after 24 hours, the amount after 24 is 100. 1/2 to the 24 over 8.1. Exact same calculation. I'm just going to bring it down and replace the 6 with the 24. So I'm going to go 2 and insert a 4 and hit enter. And we get 12.8% after 24 hours. The patient missed the 24-hour appointment, and when the doctor finally took the measurement, he determined that the patient had a healthy thyroid. If the percentage of radioactive iodine in the blood was measured at 84.3%, calculate the approximate number of hours which had elapsed since the patient was given the capsule to swallow. Okay, so we got to figure out, wait a sec, did I do this right? Oh, I messed up. No, did I mess up? I messed up. Yeah, because 6 hours, the time is supposed to be in days, right? This is where T is the time in days, and I just put 6 in there, and 6 hours is not a day. 6 hours is a quarter of a day, so let's go back and recalculate these. So after 6 hours, that's 0.25 days. Okay, so let's replace the 6 with a 0.25. 0.25. 97.88, 97.9%. Okay, so let's fix this. 0.25, 97.9%. And this one, 24 hours is 1 day. So I got to redo this calculation with a 1 now. Replace that 0.25 with a 1. And we get 91.79, or 91.8. 91.8%. Okay, I figured I messed up because I had 6 hours being 54%, and this has 84.3, so. Okay, so if we're going to do this, solve for the 84.3, we need to enter the equation. So it's 100. Let's do that up a bit. Bracket 1/2 to the power of x divided by 8.1. So x divided by 8.1. Now that's just the normal graph. So let's just look at the graph. Say 0 to, I don't know how many days. Let's leave it as 20. And y will go from 0 to 100 because it's a percent. Right? And we can just graph this and see. We're going to start at 100%, and then it's going to be, this is a declining function, right? Increasing or decreasing. Right? Remember our two exponential types are increasing and decreasing. And we want the patient to have 84.3%. And that will occur after, so we're looking for the intersection. One, two, three. 1.995 is my x value, right? Which is the number of days, 1.995, or 2.0 days to the nearest. So 2.0 days, 48 hours. Okay, so it works out to 48 hours. All right, a minor mess up. And there we go, done.